Hello and welcome back to the course on machine learning. Today we will finally find out about the kernel trick. So let's get started. So here we've got the Gaussian or the radial basis function kernel, and those are two interchangeable terms. And now let's have a look at this function. So K stands for kernel, and it's a function applied to two vectors. The x vector, so this is some sort of point in our data set, and L stands for landmark. I means there might be several landmarks, but we're not gonna worry about I for now. We're just gonna look at this as a landmark, and then that equals to an exponent in the power of minus the double vertical lines mean the distance between x and the landmark squared divided by 2 sigma squared. So I know this might all seem very confusing right now, and you're probably wondering, Kirill, this makes no sense whatsoever. What does this even mean? Well, let's explore this through a visual example. So here I've got an image which represents this particular function for a specific sigma, for a specific landmark. But this is what it looks like in a when you visualize it. And so what's happening here is we've got L, the landmark, is actually in the middle of this plane. So in the middle of this two-dimensional space, let's imagine this is the x coordinate, this is the y coordinate. In the middle, we've got 0, 0, and that's where the landmark is actually located. And then the vertical here, the vertical axis represents the result that we get when we calculate this for every other point on this xy axis, on this xy field or plane. If we take any other point, then the results of this calculation, so let's say we put that point in here, and then we calculate the distance to the landmark, and then we square it, divided by 2 sigma squared, where sigma is some fixed parameter that we decided upon earlier. And then we take the negative of that, and then we put the exponent into that power. Then we get this result, and that's what it will look like. So let's go through this step by step. Let's look at the tip of this visualization. It's right in the middle of this whole XY plane. And so if you project that back onto the plane, and the bottom, you'll have the kernel. That's or not the kernel, that's the landmark. We're going to call it the landmark. That's where the middle of this bottom square is, and that's from where we're measuring the distance. So K, this distance, x minus Li, this distance that we're squaring here, will be measured from that landmark. So let's take a point and look at it. So there's a point. It's somewhere on our plane. It's quite far away from the landmark. There's a distance. So we're taking that distance. We're squaring that distance, dividing it by 2 sigma squared, taking negative, and then we want to see what the result will be. And so how can we confirm that this visualization is actually indeed aligned with this formula? So it's pretty simple. The distance here, let's assume it's quite large, right? So it's quite a large distance compared to some other points that are closer to the landmark. So basically the distance here is a large number. And if we take a large number and we square it, right, we get an even larger number. And then we divide by 2 sigma squared. It's still, assuming it's still a large number, again, depends on the sigma, and we'll find out the role of sigma further down in this tutorial. But assuming this is still a very large number, so you've got a very large number here, and then you're saying negative, you're making it a negative, a very large but negative number. So if you take an exponent and you put it into a power of a very large negative number, so e to the power of 1, let's say minus 1,000,000, right? So, just for argument's sake, or minus 1,000. What does that give us? That gives us a value very close to 0. So it's basically equivalent to saying 1 divided by e to the power of 1,000, and that is a very, very small number. So that basically means when you're far away from the landmark or from the center, you get pretty much 0 on the vertical axis, and which aligns with our image here. Now let's have a look at another example. So this point is actually closer to the landmark, and here, if we measure the distance, it's quite small. So now if you take a small number, you square it, and you still have a small number. You divide by 2 sigma squared, you still have a small number. So you look at e to the power of minus a small number. So let's say e to the power of minus, I don't know, like or e to the power of minus 1, for example, or e to the power of minus 0.1. So that basically means, so this number is close to 0. It's as you get closer to the landmark, this number gets closer to 0. So, and we know that e to the power of minus 0.01, 0.0001, and so on. Basically, as you get close to 0, e to the power, we get closer to e to the power of 0. And e to the power of 0 is 1. So basically, as you get closer to your landmark, this number over here, this number here gets smaller and smaller and smaller, and this the whole right part over here converges to 1. So it becomes bigger, 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 and you climb this hill up to the top, where you get to 1 at the very landmark itself. So when you exactly hit on the landmark, you get to the top. And so that's just a quick way of checking that this image is indeed the kernel function that we're looking at. And why is this all useful? Why do we need this? Well, because we're going to use this kernel function to separate our data set, to build that decision boundary. So let's have a look. There is our two-dimensional space, right? And there's our x1, x2, just like we had here, x1, x2. And now what we're going to do is we're going to take the landmark and put it somewhere in our among our data set. And there's a whole methodology on how the machine learning algorithm, when you implement it in R or Python or any other language, how it does it. And we're not going to go into detail on that because we're just focusing on the intuition, but basically there's a way to find an optimal placement for these landmarks. And so the landmark is placed, and next what happens is the distance, as you can see here, the circumference around this kernel function is actually projected here onto our visualization. So what this circumference allows us to do is it allows us to take all of the points that are within that circumference and have them like assign them a value of above 0. So anything outside the circumference, all of this blue stuff, so basically all of these red points, they'll get a value of 0, right? If you apply this function, or a value very, very close to 0. If, on the other hand, any point falls within the circumference, based on this function, it'll get a value of above 0. And that is how we can separate the two classes, the green from the red. Just if we pick the right sigma, so here we know that sigma actually, well, we don't know that yet, but what's sigma's role is that it defines how wide this circumference is. So if you increase sigma, the circumference will increase. Like this picture didn't change, but it should change. The circumference here would increase and you would take more of a space up. Or if you decrease sigma, the circumference will decrease, and therefore you'll take less points. And so basically by finding the right sigma, you can set up the correct kernel function to assign 0 values to all of the points that you don't want in your classification, and values above 0 to the points that you do want in your classification. And that will allow you to separate the two. That will allow you to classify each one. And that, in essence, is the kernel trick. We have created a decision boundary without actually going into a higher dimensional space, without having to project all of our, or create a mapping function that's going to take us to the dimensional space and do all the computation. The point is, we're not doing the computations in the higher dimensional space. We're still doing the computations in the lower dimensional space. Yes, we have this visual representation that involves a higher dimensional space, but at the same time, if you look at the computational part, we were just calculating this formula, and then we're saying if this is greater, if this is equal to 0, then assign class red. If this is greater, or equal to greater than 0, then assign class green. If you look at the computation, it's actually happening still in the 2-dimensional space, and that's called the kernel trick. So all of a sudden, you can adjust your decision boundary, and it's nonlinear, and moreover, you find yourself being able to solve much harder, much more complex problems like this, for example. So here, this is it's a very simplified formula, but if you take 2 kernel functions, you just add them up. In reality, they have to be coefficients, theta here, and then another theta before. So they have to be coefficients with these, with the kernel formula. It's a bit more complex than that, but in simple terms, if you take 2 kernel functions and you just add them up, then because the value of this function, if let's say this is kernel or this is your landmark 1, because the value of the function when you get further away, it becomes 0, right? They don't really interfere. So as you move away from this landmark, so this landmark will only encapsulate all of these points around here, and then as you move away, this will be 0 everywhere, right? Everywhere else, including in these points. But then this one will be non-zero close to this landmark. And so if you just add them up, you will get non-zero values for exactly all of those points. And so therefore, you can draw a nonlinear decision boundary, which even looks like this. And the formula here would be the point is assigned to the green class when this equation is greater than 0, and the point is assigned to red class when this equation is equal to 0. Now, again, this is a very simplified example. In reality, this is a bit different. It's greater or equal to 0. This is less than 0, and that's because we have the coefficients, and it is a bit more of a complex mathematics behind it, but we don't really need to go into those depths. The point is that we understand here that we can create this non-linear, very complex decision boundary without having to go into a higher dimensional space. Everything is still happening in those same dimensions simply because we're applying the kernel functions. And that is why this method is called the kernel trick. I hope you enjoyed this explanation, and I look forward to seeing you next time. Until then, happy analyzing.